Imagine a car where the battery isn't hidden under the floor or confined to a compartment. It's actually in the body of the vehicle. This idea, which seemed like science fiction until recently, is becoming a reality with the advent of so-called structural batteries. The proposal is simple but powerful. Transform the car's physical structure into a power source. Instead of charging a battery, the car ran the battery. And we're not talking about a distant concept. Several laboratories around the world are putting this into practice, with results that are already shaking up the automotive industry. These batteries are made from materials such as carbon fiber, already known for its lightness and strength, combined with solid or semi-solid electrolytes that allow the flow of ions. This combination creates structures that support the vehicle, but also store and supply energy to the electric motors. The result is a chassis that not only withstands impacts and protects occupants, but also guarantees the car's range. Instead of using two separate structures, one for resistance and one for energy, engineers now consider a single structure, which means less weight, greater efficiency, and freed-up interior space. Lightness is one of the biggest advantages here. Since the vehicle's structure is no longer composed of heavy metal parts and a traditional battery weighing hundreds of kilograms, the car loses significant weight. And when it comes to electric vehicles, every kilogram lost represents more autonomy on the road. According to computer simulations, a mid-size car with this technology can travel up to 70% further on a single charge. This isn't just a vague promise. Data is already emerging from laboratories and taking shape in real prototypes, tested under a variety of conditions. Another interesting point is how this solution frees up interior space. In many current models, the battery takes up much of the space under the floor, forcing a higher height or a limited design. With the battery fused to the structure itself, there's freedom to reinvent vehicle design. Engineers can now imagine lower models, more spacious interiors, or even shapes that would previously have been unfeasible due to the limitations of traditional batteries. What was once a physical barrier is becoming an open door for innovation in automotive design. And the impact isn't limited to designers. From an industrial perspective, merging the frame and battery into a single component could greatly simplify the assembly line. Instead of assembling a chassis, then placing a battery inside, and only then fitting everything together, manufacturers could produce single parts that are faster to manufacture and assemble. Fewer parts mean fewer screws, fewer robots, and fewer points of failure. This reduces costs, speeds up production, and can even help make cars cheaper in the long run, all while improving performance. What's most striking about this revolution is the speed with which scientific advances are paving the way for structural batteries to move from paper to the streets. Two of the world's most respected research centers are at the forefront: KAIST in South Korea and Chalmers University in Sweden. These two institutions have been leading a quiet but intense race to increase the energy density and resistance of these materials to unprecedented levels. And unlike so many technologies that remain stuck in laboratories, the prototypes they developed have already undergone real-world testing with impressive results. In the case of KAIST, the focus is on a highly dense carbon fiber composite, combined with a specially vacuum-formed solid resin. This process eliminates the air bubbles that, in previous designs, weakened both the structure and electrical capacity. The result was a remarkable leap, a 160% increase in carbon fiber volume compared to previous versions. And this not only made the material lighter and stronger, but also more efficient at storing energy. It's as if every inch of the structure had been turbocharged to work twice as hard, supporting weight and conducting energy simultaneously. At Chalmers University, the approach was slightly different, but equally promising. There, engineers managed to transform carbon fiber itself into active electrodes. In other words, in addition to providing structure to the vehicle, it also directly participates in electrical conduction. To complete the system, a type of structural electrolyte runs through the composition. allowing ions to flow as they would in a conventional battery. Current energy density is around 30.2 still below traditional lithium-ion batteries, but a huge advance compared to what existed just a few years ago. And what's impressive is that these materials aren't just being tested under ideal laboratory conditions. In experiments simulating real-life situations, such as pothole-like impacts and constant loading and unloading stresses, the prototypes demonstrated surprising resilience. A structural panel was subjected to more than 3,500 deep load cycles, while simultaneously being stretched and compressed as if it were facing the uneven asphalt of a busy city. In the end, the capacity loss was only 15%. For comparison, conventional batteries typically reach this level after one-third of use, and without any mechanical impact. These figures have caught the attention of even the most conservative sectors of the automotive industry. After all, it's not just about range or lightness, but also about reliability. No one wants to drive a car whose battery can crack or deform after a minor collision. With current lamination techniques and the use of electrolytes that don't deform easily, researchers are creating batteries that can literally take the hit. The ability to maintain structural and energetic integrity under physical stress is precisely what transforms a good laboratory idea into a real everyday solution. What perhaps few people have realized is how far this technology can extend beyond the world of electric cars. The idea of a structure that also stores energy doesn't need to be confined to the four wheels. Researchers and engineers are already testing applications in everyday products, like laptops and smartphones, with results that, at first glance, seem too absurd to be real. But they're not. A laptop with a battery case can weigh half its current weight and still last the same amount of time. It seems like magic, but it's just carbon fiber engineering and clever energy distribution. In the case of cell phones, the advances are even more striking. The first generations of structural batteries created by Chalmers already allow the construction of a functional case just 0.8 mm thick. Translated into the real world, this means smartphones less than 4 mm thick, practically the size of a credit card. And most surprisingly, this happens without sacrificing usage time. What once seemed like a physical limitation, after all, you can't make a battery smaller without losing capacity, is now being overcome with an entirely new approach, where the device's body becomes part of the power system. In aviation? Well, if there's one industry obsessed with weight reduction, it's aerospace. Airplanes and drones struggle with every extra gram because it directly affects range, fuel, or energy consumption, and even flight safety. Imagine replacing parts of the fuselage or wings with materials that, in addition to withstanding aerodynamic stress, also provide power for onboard systems. Several drone prototypes have already been built with this approach, and the results are promising. Greater autonomy, greater payload capacity, and reduced need for extra batteries on board. It's as if every inch of the drone is working to generate power. It's no exaggeration to say that this change could completely reshape the shape of electronic products and vehicles. By eliminating dedicated battery compartments, there's room for more features, more components, or even thinner, lighter, and more elegant designs. In laptops, for example, this could pave the way for foldable, ultra-thin devices or devices with larger cooling areas. In drones, it could allow for the installation of heavier sensors or more robust communication systems, without having to compensate for the weight with larger batteries. Another relevant point is that this new energy architecture allows us to rethink device durability. Because energy is embedded in the structure, the chance of failures due to deformation, breakage, or localized impacts is reduced. Instead of a sensitive battery module that needs to be protected, the battery is now the shield itself. This is particularly important for electronics manufacturers who want to create more durable, waterproof devices with fewer moving components. Fewer parts means fewer failures, which also translates into fewer replacements and disposals, a positive point when considering environmental impact. When it comes to extreme performance, it's impossible to ignore the real-world challenges traditional batteries still face. Problems like swelling during charging, dendrite formation that causes short circuits, and accelerated capacity loss over time continue to be a nightmare for many manufacturers. And here's another powerful advantage of structural batteries. They simply don't suffer from these same defects. This is thanks to the use of semi-solid electrolytes that don't expand with heat, don't leak, and, most importantly, don't create unstable zones within the structure. Reliability becomes an ally of performance. Furthermore, these batteries handle physical deformations much better. If a car experiences an impact, a light bump, or even a twisted body, conventional batteries run the risk of internal cracking. Structural batteries, with their interwoven carbon fibers distributed in stress-absorbing patterns like a kind of energy fabric, maintain electrical integrity even in adverse situations. They function almost like a rubber band, flexible enough to withstand pressure, yet firm enough to continue operating without failure. Tests in extreme climates also revealed above-average performance. In freezing environments like those of Minnesota in the winter, prototype vehicles with structural batteries maintained up to the autonomy is 91% original, while cars with traditional lithium-ion batteries lost up to 28% of their capacity. This is because the semi-solid electrolytes used in these batteries don't become viscous like liquids, maintaining the fluidity of the ions even at sub-zero temperatures. The practical result is that the car continues to run smoothly, even when the cold tries to freeze everything around it. Another aspect that has sparked interest among engineers and consumers is fire safety. Everyone has seen news reports of electric cars catching fire after accidents, often due to leaking flammable electrolytes. With structural batteries, this changes completely. Because the electrolyte is semi-solid, it doesn't leak or form flammable vapors. What's more, the carbon fiber structure itself acts as a sort of Faraday cage, dispersing heat and preventing it from concentrating in critical points. This drastically reduces the risk of spontaneous ignition. The impact tests went beyond traditional ones. Sections of these batteries were subjected to simulated explosions with metal shrapnel at 200 meters per second, a speed higher than that of many urban accidents. Even so, the worst damage recorded was a shallow crater that didn't even reach the internal conductors. This shows that, in addition to being efficient and durable, these batteries may be the safest ever developed for use in vehicles of all sizes, from scooters to trucks. All this robustness also translates into long-term durability. One of the biggest concerns for electric car owners is battery degradation over the years. But with materials capable of withstanding intense charging cycles and resisting microscopic cracks, often with self-healing properties, vehicles equipped with this technology promise not only greater short-term range, but also a significantly longer lifespan. This changes everything. Less maintenance, greater safety, and a future with fewer batteries discarded due to premature failure. Amidst so much innovation, one question is beginning to emerge more forcefully. Who will be the first to make all this a reality on a commercial scale? And the answer already has a familiar name: Tesla, Elon Musk's company. Known for anticipating trends and pushing the limits of what's possible in the automotive industry, has already begun applying the concept of structural batteries in its latest vehicles. While not yet the full carbon fiber model seen in laboratory prototypes, the Model Y and Cybertruck already represent what many consider the first practical step toward this new era. Rather than simply adding batteries to an existing structure, Tesla is incorporating the battery modules themselves into the car's structure. This drastically reduces the number of parts, eliminates extra brackets and bolts, and makes the body more rigid. Furthermore, this integration helps lower the vehicle's center of gravity, which improves handling and cornering safety. Energy efficiency increases, comfort improves, and production becomes more straightforward. Fewer steps, fewer robots, less complexity. All of this is a preview of what could come with the full application of next-generation structural batteries. This approach is even changing the way Tesla's factories are designed. By rethinking the vehicle as a single piece, or as Musk likes to call it, a unified body, assembly becomes more like fitting blocks together than a jigsaw puzzle full of fragile parts. With fewer components, the chance of error decreases, production times shorten, and costs can fall. For a company that already leads electric vehicle manufacturers in profit margin per car sold, this represents another step toward industry dominance. But perhaps the most interesting thing about this story isn't just Tesla's use of this technology, but rather the ripple effect it has on the competition. If a giant like Tesla can put lighter, safer, and more autonomous cars on the streets while reducing production costs, the rest of the industry will be forced to follow suit. And that's where structural batteries come in as a game changer. It's no longer about launching the prettiest or fastest car, but about creating a completely new energy platform that makes everything that came before it obsolete. The presence of this innovation in commercial models also serves as a living laboratory. Every kilometer driven by a Model Y with an integrated battery provides valuable data on performance, wear, thermal behavior, and potential structural failures. This information fuels constant improvements, refining the technology for future releases. And with Tesla's rapid pace, able to test, adjust, and implement changes in a matter of months, the leap from the current stage to a vehicle with a full structural battery could happen faster than the market imagines. And if anyone still thinks this is all a distant idea, just remember one thing. Today's cars already carry parts of this revolution under the hood. What's missing now is the next step, the definitive replacement of traditional batteries with advanced energy composites, the complete fusion of structure and power. The future is still under development, but the foundations, or rather, the structures, are already rolling down the roads.